Hello, I'm Steffen Wenzel, and I'm presenting you our paper, A Generic Taxonomy for Steganography Methods, which was published by ACM Computing Surveys. It's a paper authored by 11 authors from several affiliations in 4 countries. And it's a long history behind this paper. Actually, research on this started around 2013 um, and led to a network-specific taxonomy, which finally evolved into this broader taxonomy in 2025. Scientific reinventions are a term to describe ideas that appear multiple times in research. And that means someone has an idea, it's published, and maybe neglected or just recognized in one domain, but not in another, and then it's reinvented from someone else who just doesn't know the other domain. And yeah, that's called a scientific reinvention, and cybersecurity is no exception from this problem. More on reinventions in cyber security and in computer science in general can be found in our paper Avoiding Research Tribal Wars using taxonomies on the right side of the screen. Um, so the idea here of this paper is to derive commonalities of the different steganography domains. Steganography is the art and science of how data can be hidden in some other data. For instance, a video can be hidden in another video, or a textual message can be hidden in an image or in a network packet. Now, let's start with a quote, Donald Knuth. In my own field, for example, it was once possible for a grad student to learn just about everything that was to know about computer science. Nowadays, that means 2001, when the book was published, nowadays the subject is so enormous, nobody can hope to cover more than a tiny portion of it. So that's quite alarming, because that also means that it's becoming increasingly difficult to remain, to keep an overview of what's actually happening in a scientific domain. And what this is described here for computer science is true for cybercrime as a subdiscipline and steganography as a sub-subdiscipline. Um, and we addressed that starting in 2014 and 15 with a pattern-based taxonomy for network covert channels, or in other words, for network steganography. This was the root publication, and the concepts of this work still remain the idea of using so-called design patterns, and lots of the terminology is kept through the years. It's still valid, and what I present today is still backwards compatible to the 2015 edition of this taxonomy. So this was a key publication, or the key publication at the start, and then we had a textbook published with a modified version of the taxonomy, and then another modification, and then some new additions to the taxonomy, new patterns, etc. Hildebrand et al. Applied the taxonomy and modified it to the ICS context. Mileva et al. Added a new pattern, and so forth. In 2021, we published an intermediate version, a revised taxonomy, already with, I think, 10 authors. And then some follow-ups appeared. The first taxonomy for indirect hiding methods appeared also in 2022. Schmidbauer and myself published that. And finally, this year, this generic taxonomy. So while there are a few papers under review, and the original taxonomy was quite technical. The question is, what does that mean to have a generic taxonomy for steganography methods, and why is this new? So the idea is that we want to draw links between the different subdisciplines and find common terms. For instance, someone might have an idea how to describe a hiding method or invents a new hiding method in file system steganography that is similar in cyber physical systems steganography, text steganography, or network steganography. So they could use the same term, or at least better understand what someone else is doing in a slightly different domain, and then benefit from each other, combine their ideas and research methodology. So we find common terms for this, and we want to aid the development of the whole steganography domain, including all the subdisciplines that it has. This is the 2015 taxonomy in its latest version. As you can see, it's quite a massive piece, much more complex than what I will present uh, with the new taxonomy a few slides later. This is still valid and, as mentioned, backwards compatible, but before I go to discuss the actual taxonomy of 2025 for the generic view, let's start with some problems. Because there are many taxonomies available. Why doing another one? First of all, we need to agree on common terms in science so that we all know what we are talking about. And also to keep the knowledge alive. In biology, this has probably the longest history, and maybe besides philosophy, and was very was attractive to many researchers, so it was kept alive. Even the terms that were initially described and used and invented by Carl Linnaeus. And however, the problem that we have is that we have many different terms in steganography. Let's just keep an example of network steganography, where the modulation of packet sizes can be used as a covert channel. But if we search for that, we find many different terms. For instance, size-based covert channel, packet length covert channel, packet size covert channel, field length covert channel, or padding size covert channel, but they are essentially all the same thing. So the solution that was already proposed in 2015 in the first paper is to use aliases and apply a common unified description method called patterns in a unified language that was PALML or PLML, the Pattern Language Markup Language, version 1.1. That works because we can then link patterns to each other and have a unified structure for their description. That's nice to have. So we apply aliases. Okay, then we have solved somehow the issue that different things are described with the same name. But who cares about yet another taxonomy? They are published on a regular basis. Most of them are neglected. Nobody cares. So we face the same issue. The solution is that we involve the community. For instance, if you find a new pattern, so then a new idea how to hide something and something else in steganography, get in touch with us. We will add your paper to the taxonomy, to the website. We will reference your paper. If you, and also, of course, you will be named as the inventor of the pattern. If you publish work that matches some pattern and add some new findings to it, a new implementation or whatever, paper code data, we will refer it on our website for the taxonomy. So this attracts attention to your work as well. And we have the benefit that the taxonomy becomes more complete. If you plan to contribute something fundamentally fundamental, just contact us. Then it's that people need to understand the taxonomy. So it must be accessible. And Linnaeus did something that helped his own taxonomy to gain a lot of visibility and popularity. And that is a binomial nomenclature. So that means that essentially we describe things with two terms, like Canis lupus, which is the gray wolf. And if we want to become more specific, we add just more terms to it, like Canis lupus dingo, the Australian dingo, or Canis lupus familiaris is the common house dog. So there's a simple before, and you can extend it with more terms to become more specific. And that's what we also apply here. Let's take a simple example. We can have some state or value that we modulate somehow. We can do this using the least significant bit algorithms. So we call this LSB state value modulation. And we can do this in the network. So we call it network LSB state value modulation. That's straightforward, and so is the enumeration. Then the issue is we have pretty different objects in which we want to hide data. Images, physical environments, text, network traces, file systems, and still the taxonomy should be exhaustive and mutually exclusive. So that means that every object should be classifiable, but only belong to one class. And the issue is here that there's a clear overlap. As you can see here, network steganography, text steganography, and CPS steganography can easily be overlapped. For instance, if I modulate a text character in a network transmission, then somehow this is text steganography, but it's done in a network, so it's network steganography. So there is an overlap. If that's a set point for a cyber physical actuator, then it would even be also CPS steganography. And that means we can find a general term for that. Because what we modify here, the character's case, like making a lower or uppercase character ABC, is a character case modulation somehow. That's it. Previously, we had a little bit complex structure that you can see here. We discarded that, so let's skip that. We have a keep it simple and stupid approach. And essentially, we have elements. Elements have a state or a value. An element could, for instance, be an inode in a file system that can have a state like it's existent or not existent. It can have sub-elements, for instance, an inode number, and that has a state or value in that case, and that's the number itself, and so forth. So elements can have sub-elements, and each element has a state or value. Here are a few examples. I won't go through all of them to prevent boring you, but you can pause the video here if you want to get a few examples. Here's a little bit more example plot or visualization of a flow in a network. So the flow is an element containing packets. And the flow has some virtual and real attributes like number of packets, flow duration, and the packets themselves. Each packet has, again, elements like the version of the IP header, the IP header length, and so on. So the packet has a virtual attribute that would be time of occurrence, maybe more virtual attributes, and it has these attributes here or elements. They can, like the options element again, have sub-elements that can again have sub-elements that again can have sub-elements. And for these, we can always define some virtual attributes like number of options or entries or whatever, and then the values of each of these elements. So at an abstract level, it doesn't matter if I modulate the value of a sub element or some meta element. That's our view. So it's a very generic view. Could also be the content of a file. Okay, problem 5. Hiding methods are often hybrid, and that was neglected by previous taxonomies. So let's take the artificial reconnections hiding method. The idea is that a sender triggers reconnects of some clients in a network and a receiver monitors that. And the order in which the clients are reconnected indicates the secret message. So what happens here? The sender, in order to transfer the message, needs to modulate some value So some bits in network packet headers that cause a retransmission, but it must also act in a timely fashion because it matters which client is disconnected first and next and so on. So the sequence matters. So it's also an element positioning idea. That means the element, the reconnect element, it's a virtual element in that sense, occurs at some point in time, and we position that element in time. That's why it's called element positioning. So the solution is that we allow hybrid definitions combined of atomic elements. Let us digest for a second. The idea is just pretty simple in the end. We break down our actions to an elementary level while remaining abstract. And we say that some methods combine multiple approaches. So we don't categorize this hiding method into one pattern, but it actually contains two, or is based on two. And another aspect is that extraction and embedding process might use different techniques. Take an example, Kovaceanu by Spiekermann et al., where a sender relocates the position of a virtual machine around the globe. For instance, the virtual machine could be migrated from a computing center in Australia or Europe to Australia using some commands. So it's some state value modulation of some commands. But the receiver, in order to measure the secret, to obtain the secret message, needs to measure the round trip time, because the round trip time might encode indirectly through the location of the sender the secret message. So that's an element positioning again, because we need to measure the temporal position. And that's why we decoupled embedding and extraction process. In the paper, there are many examples that illustrate this. Also, look at the electronic supplement, where we have more examples and where we transfer all the previous patterns into the new ones while featuring exactly such examples. So the embedding patterns describe how the secret information is embedded into the cover object, for instance, a file or a network packet, while the representation pattern describes how the secret information is represented by the cover. And here is the new taxonomy. And as you can see, it's way less complex than the previous one. So every method is reflected by a hiding pattern. And we have the embedding patterns, and derived from them are representation patterns. They are essentially the same. Anyway, we just have two core pattern types, namely the state or value modulation. State could be a temperature, value could be, well, some value of a protocol field in a network packet. Or we have the element occurrence. The star property is just for extensions. It's currently unused. If we modulate the state or value, we can modulate reserved or unused values, random values, least significant bits, characters, or the redundancy, for instance, by means through transcoding steganography. If we modulate the occurrence of an element, we could modulate its enumeration. So an element that describes the quantity of sub-elements. For instance, an image file or a text file could have 100 or 101 bytes. A network packet could have 100 or 101 bytes, and so on. Or the IP options header could include 0, 1, or more than one options. Or the IP version 6 extension header could contain the IP version 6 header could contain extension headers of arbitrary number. The element positioning means that we modulate an element that describes the positional value where an element occurs. For instance, where in a flow does a specific network packet occur? Where in an image does a specific pixel value occur? Where in the list of options does a specific option occur? Things like that. Let's go through some examples for the different stego domains. In network steganography, one method is to use TCP retransmissions. That means we send duplicates for packets, but artificially. That would be network element or enumeration because we enumerate the specific network packet. It occurs twice instead of just once. In CPS steganography, we would encode a secret signal by influencing the response of a CPS actuator. So we could cause a delay. Let's say I want to send a command to open a door or a window, and I could delay the response. That would be CPS element positioning, because again, we position something in time. In file system steganography, a typical method would be to use unused file system blocks to insert or embed secret bits into these blocks. So that would be file system reserved unused state value modulation. So we modulate a value and that's currently unused and it's in the file system. So it's file system reserved unused state value modulation. Text steganography, we could modify the features of characters, for instance, underlining something, making it italic, and that would be text character state value modulation. In digital media, we could insert a blue screen or blue pixel at some location in a video or image file, and it would be digital media element positioning. Although digital media has very rich methods, we can break down these methods on this abstract level in very few patterns as well. But as you will see later, we have foreseen subtaxonomies for the different stego domains. However, I want to point out this also works for side channels and networks. For instance, a side channel described by Schinzel, where the response time of a target depends on the existence of a username. So I send my credentials, username so-and-so, password so-and-so. And if the username exists, the database needs to check whether the password also matches. That consumes extra time, and that would be a side channel that can be measured. So the delta T, the time between sending the request and getting the response, could be measured by the attacker. And that would be network element positioning because the response element, the response packet, is positioned in time by the side channel. So yes, this taxonomy would also work for side channels, most likely also for hardware side channels. And another idea is to use the taxonomy for traffic obfuscation or censorship circumvention, for instance. In Peekaboo, traffic padding is analyzed, and traffic padding can obfuscate the characteristic of a flow in a sense where someone tries to identify the type of flow that we see. Is this a Skype flow? Is this a chat flow? Is this some typical browser session? And the packet size is modulated, so it would be network element enumeration because we enumerate the additional padding bytes. Alrighty. Now that we've learned about the generic taxonomy, I want to point out a few more things. So there's no one-fits-all solution. It's a generic taxonomy. This is not about sophistication. This is not about optimizing embedding. However, we have foreseen domain-specific taxonomies, see the paper, that can be extended with more sub-patterns and so on. So feel free to propose additional sub-patterns for these sub-taxonomies, etc. And for the very detailed things, because the taxonomy is usually quite generic, you might want to also describe things like channel capacity, detectability, robustness, things like that. we have foreseen a unified description method. Actually, that's based on the paper that you see here, Unified Description for Network Information Hiding Methods, where we analyzed more than 100 described hiding methods, 131 described hiding methods in the literature, and found that their descriptions vary a lot. So, for instance, the robustness is checked by very few, capacity by around half of them. And also an application scenario is not always provided. We modified this approach slightly, made it a little bit more compact, but the previous approach is still valid, and but this one has the advantage that it separates the embedding from the hiding process, because we split the embedding and the extraction process in our patterns. And for this reason, it's easier to use this revised model that we have foreseen. You don't find this in the paper. You find this in the electronic supplement of the paper. And also featuring some examples that you can learn from. So you can use this description method in your paper to aid the replicability of your hiding method that you describe, because then others can easily see what you have done and what can still be enhanced. For instance, which application scenario do you foresee? What's the properties of the cover object that you foresee, and so on. And they can potentially change things or enhance things. All right. Will people use the taxonomy in the right way? Hopefully, we have foreseen several design rules that I won't bore you with at this point. Have a look at the paper. We took care of a lot. Backwards compatibility, problem 9, that's the last problem. We took care of that as well. As you can see in these tables, they are taken from the paper. All the previous patterns can be transferred into the new ones. Some become hybrid patterns, some remain patterns as they are. The terminology is pretty much overlapping or at least linked, so it's easy if you worked with the previous taxonomy to work with the new one. And you might say, well, hybrid patterns is a fine thing, but you should take more care of indirect hiding patterns. That's true. But we already did a taxonomy on this, and it's can be found in the paper ZOC, a survey on indirect network cover channels, but it's not really network specific or limited to the network context. You can use this in other contexts as well. We have foreseen these 3 patterns there, and they can be referenced in the unified description method as well. What else can be done with the taxonomy? Well, we can evaluate what's new, first of all. So we can check, did someone already has had the same idea and maybe just use different terms? We can categorize and describe what exists in terms of hiding methods, and we can identify gaps much more easily. So research gaps that can be filled by new students, especially because we determine that something is not representable by existing patterns, or we find hints in describe in papers that use the unified description method, because we see, okay, they describe that and that, but they lack that and that. So this is the main purpose of the taxonomy, besides the linking, the takeaways. We wanted to categorize all methods in steganography. That's why this taxonomy is very broad, it's abstract, it's a high-level thing. With a 3-tier approach, so that you can also refer to specific and detailed aspects of hiding methods. We can handle indirect hiding methods, and we've solved several problems that taxonomies usually have. The key message is a large fraction of research and information hiding overlaps. And we think that it was necessary to find common terms for that to prevent or minimize scientific reinventions in the future. And one taxonomy might be the solution for that. If you want to figure out more or download the paper, visit our website or download the paper directly. Keep in mind, the electronic supplement contains many information not included in the main paper due to page limits, like the unified description method. Thank you for your attention.